Right. So try this question. Assume there is a resistance of say 20 ohms, and the current passing through the resistor is 2 sine 100 pi t. Okay, so the alternating current passing through a resistor is given to you. Based on this, derive the equation for alternating EMF and then average power dissipated by the resistor. Okay. Yeah, Rishi, good evening. We just started the class. This is the first question.
Good evening, sir. Okay, sir.
So across or through this resistance of 20 ohms, this much current is passing. Derive the equation for the voltage across that resistance and the average power dissipated by it. Try. Okay. Rishi, can you tell me the idea? How will you write an expression for voltage across a resistance if you know the current and the resistance?
Sir, so to calculate E over here, we have to, the equation is 2 sine 100 pi t. So will we,
Like just the idea, you know the current through the resistance and you know how much resistance is there. How will you write or how will you calculate the voltage across the resistance? Isha, can you tell?
sir, Ohm's law, V is equal to IR.
That's all. Correct.
Yes, sir.
Correct. Okay. So just multiply them. What does it become equal to? Okay, let's not
40.
waste much time. 40 sine 100 pi t. Okay, the current is variable. Multiply with resistance, the voltage will also be variable. Okay, so an alternating voltage will appear across that resistance. And how will you calculate the power dissipated, average power dissipated by a resistance?
Sir, it's 2 by root 2. I think, I'm not sure.
Tell me the formula.
Yeah, sir.
E naught square
It's
by 4.
E naught square by 2R. Yes. You can even use I naught square into R. Okay. You can also use E RMS square divided by R. You can also use I RMS square multiplied with R. Any one of these will give you the answer, and they'll all give you the same answer. Okay, let's randomly choose one, maybe the first one itself, E naught square by 2R. E naught, peak value of EMF, that's 40 squares, 1600 divided by 2 into resistance is 20. So this will be 40 watts. Okay, any doubt in this? Simple.
No, sir.
Yesterday what we did was, based on EMF, we wrote the current equation. Now based on current equation, we are writing the voltage equation and then calculating power. Okay. Fine. The next thing you need to learn is what happens when an alternating EMF, E is equal to E naught sine omega t. Let's take the simple EMF equation. Okay, you need to learn what happens when this EMF is applied across a capacitor. Okay, yesterday we looked at resistor, today capacitor and inductor cases we'll discuss. Now tell me, when alternating EMF was applied across a resistor, what was the phase difference between current and EMF? Were current and EMF in phase, or did they have any phase difference?
They did have phase.
They did. How much? Okay, you look at this equation itself. Current through the resistance is known, and the voltage across the resistance is known. Fine. And they both have the same sign function, right? Sine 100 pi t, sine 100 pi t. There's not even any minus sign outside or anything. So when this becomes +1, when this sine function goes to +1, this sine function also will go to +1 at the same time. Rishi, do you agree or not?
Yes, sir. Yes.
That means when current reaches the peak value, voltage also reaches the peak value at the same time. When this goes to -1, this will also go to -1 at the same time. That means they will vary similarly in phase with each other. They don't have any phase difference. If two oscillators reach the positive extremes at the same time, reach the negative extremes at the same time, and have the same time period, they are said to be in phase. Isha, is this clear? And Rishi also, did you understand?
Yes, sir.
Okay. So the voltage across a resistor and the current passing through it won't have any phase difference. Now let's see what happens when you apply this voltage to or across a capacitor. Assume there is a capacitance C and you connect an alternating voltage to it. Basically, what happens when you apply a voltage across the plates of a capacitor? Generally, alternating or not, or okay, consider direct voltage only, constant voltage.
Current flows through.
Suppose you had something like this. Let's say a battery of EMF V is connected to a capacitor, capacitance C. What will happen? Rishi, you are saying current flows through it. Current will flow definitely. And finally, what will happen? Or will current keep on flowing?
No, sir. No.
When will it stop?
When like it's equal, like the potential difference.
Potential difference becomes equal to V. So the potential difference across the capacitor plates becomes equal to V. The charge on the positive plate will be plus CV, Q is equal to CV, and on the negative plate will be minus CV. Once that happens, the current will stop, the charge flow will stop. Okay. And if there is no resistance, or if resistance tends to 0, this will happen almost instantly. Okay. If there is any resistance, significant resistance, then it will take time for the charge to get accumulated on the capacitor. If there's no resistance, this will happen instantly. Okay. In fact, we had derived the equation also, charging equation, charge on a capacitor. Q is equal to CV into, I think we had 1 minus e power minus t by tau, tau being RC. This is the equation we had, charging equation. When t is 0, e power 0 becomes 1, 1 minus 1, the charge is 0. As time passes, this term will decrease and the charge will tend to CV. It will slowly grow to CV. In fact, to become equal to CV, theoretically, it will take infinite time. But if resistance tends to 0, if there's no resistance in that circuit, here, look at the power. Okay. Denominator is tending to 0, means this whole thing will tend to infinity. But there's a minus sign. That means e power minus infinity. That means you have e power minus infinity here. E power minus infinity is 0 or tends to 0. Therefore, charge almost immediately becomes CV. It won't take much time. Okay. So you get Q is equal to CV. Fine. So if the voltage is V, a fixed voltage, you'll see a fixed amount of charge on the capacitor. But see what we have done now. We have connected an alternating voltage to the capacitor. Okay. A voltage of this form, E is equal to E naught sine omega t. For some time, the left terminal will be positive and the right terminal will be negative. Then what will happen? The left plate will get positive charge and the right plate will get negative charge. But after half cycle, the polarity of the alternating EMF will reverse. Left side becomes negative and right terminal becomes positive. When that happens, in the capacitor also, on the left side you will have minus Q, on the right plate you will have plus Q. So the charge on the capacitor keeps varying. For some time, positive charge will flow clockwise, or you can say electrons will flow anti-clockwise. And for some time, electrons will flow clockwise. They'll keep reversing the direction of flow. Current also will keep reversing the direction of flow. Fine. See, if you want the left plate to become positively charged, current will have to flow this way. That will happen for half of the cycle. After that, the right plate has to become positively charged. Then the current will have to flow this way, anti-clockwise. So the current will keep reversing its direction. So an alternating current will be produced. Okay. What we need to do now is derive an equation for that alternating current through the capacitor. And looking at the EMF equation and the alternating current equation, we should tell whether they are in phase with each other or not. And then find out what is the energy stored in the capacitor. Now see, the charge on the capacitor keeps varying because the voltage is varying. And the energy stored in a capacitor depends on the charge. And if charge is varying, the energy stored in it also will vary. Then we'll be interested in finding out the average energy and such things. Okay. Fine. So let's see how to find out the current equation. Just a moment. At a random instant, let's assume this is the situation. Let's say the charge on the capacitor, left plate of the capacitor is Q, right plate is minus Q, and a current I is flowing like this at some random instant. Our aim is to derive an equation for the current. Now, in case of resistance, we could use Ohm's law, V is equal to IR, we directly got the current. But in case of capacitor, we don't have an equation for current through a capacitor based on the voltage. So can one of you tell me an idea how we can derive current as a function of time here? How can we derive current in this loop as a function of time? Think of what we know. We know the capacitance and we know the voltage applied across the capacitor. How to get the current equation from these? Okay, one of you tell me, From capacitance and voltage, from C and V, what can be derived? Or what can we find out about the capacitor? From capacitance and voltage.
The potential difference between both plates.
Potential voltage means potential difference only. If the potential difference is known and the capacitance is known, what can be calculated?
The charge.
Charge, correct. What is the equation? How are they related?
Q is equal to CV, and then C is equal to Q by V.
Why will we do C is equal to Q by V?
Yeah,
Okay.
yeah.
Q equal to CV. Okay.
Yeah.
C, if C and V are known, you can calculate Q, charge on the capacitor. And see, the current in this wire is what changes the charge on the capacitor. You can directly see the circuit and tell. Based on how much current is flowing, the charge on the capacitor will vary. So once we get the equation for charge as a function of time, we can try to relate that to the current in this branch. That's the idea. Okay. Rishi, did you understand?
Yes.
Isha, is this clear?
Yes, sir.
Okay. So the voltage we applied is an alternating voltage, E naught sine omega t. It keeps changing with time. So the charge also keeps changing with time. So tell me, or okay, let me write it directly. Q is equal to CV. In this case, we'll write Q is equal to CE, the alternating voltage. So that becomes C E naught sine omega t. That's all, very simple. That's the charge on the capacitor as a function of time. At any time, you can tell how much charge it holds. And if you can tell how much charge it holds, you can tell how much energy it holds. Okay, so it's very simple. Now from this, we have to get the current equation. Now you see, the branch is directly connected to one plate of the capacitor. So this current is the rate of change of this charge. You can directly say I is equal to dq by dt. Because if 10 coulomb per second is flowing in this branch, okay, if the current flowing is 10 coulomb per second, like 10 ampere, then this charge increases at a rate of 10 coulombs per second. Fine. 10 ampere is a large current actually, but let it be just a random value that I considered. So we can say I is equal to dq by dt. You need to differentiate this equation of charge. C E naught are constant. C is the capacitance. E naught is the peak voltage. BA omega from alternating generator. Okay, that's a constant value. So you just need to differentiate sine omega t. Can one of you tell me the derivative of sine omega t? What is the derivative of the simple sine function?
Cos, sir.
For a simple sine function, it will be cos. But what if there is something else inside the sine bracket?
Cos omega t will become.
No. Derivative of sine x with respect to x is cos x. But if you have to differentiate something like, let's say, sine kx with respect to x, what should be done?
Cos omega t into omega.
You'll have to apply the chain rule for differentiation. You differentiate the sine function, it becomes cos kx. And then you have to differentiate what is inside the sine function also. Kx derivative will be k. So in this case, coming back to the derivation, it becomes C E naught sine omega t. If you differentiate with respect to time, it becomes cos omega t multiplied with derivative of omega t, that is omega. Therefore, the current through the capacitor or current in the branch consisting the capacitor as a function of time will be C E naught omega cos omega t. Okay. Are the steps in the derivation clear so far? We knew the capacitance, we knew the EMF that is applied across it. Based on capacitance and EMF, we first got an equation for the charge on the capacitor. And then since the wire is directly connected to the capacitor, no junctions in between, this current itself will be the rate of change of this charge. So we are using I is equal to dq by dt to derive the current equation. So this is the charge equation. Both are important. And these are not things that you remember, okay? You have to understand the logic behind this derivation. We knew voltage and capacitance, so we got the charge from it. And from charge, by differentiating charge equation, we are getting the current equation. Okay, so don't try to memorize these equations. Understand how they are derived. Okay. So observe what we got here. The EMF equation was of this form. E is equal to E naught sine omega t. But we got the current equation in this form. I is equal to some constant C E naught omega, right? This constant C E naught omega, let's call it as I naught, because that will be the maximum value of this function. As time varies, cos omega t may vary from -1 to +1. Let it be. But when cos omega t becomes +1, that's the maximum value, the current will become I naught. So I naught is the peak current. So let's take I naught is equal to C E naught omega. Okay. Then you can write the current equation that we obtained as I naught cos omega t. Okay. Can one of you tell me how to convert cos to sine? Cos theta can be written as sine of what? Cos theta can be written as sine of what?
180 plus theta.
Sine of 180 plus theta. No, 180 is an even multiple of pi. Sorry, 180 is an even multiple of pi by 2. Sine 180 plus theta becomes minus sine theta. It won't become cos.
So 90 plus theta, right?
Okay, you are saying sine 90 plus theta. Yeah, 90 plus theta takes it to the second quadrant. Second quadrant, sine is positive. And since it's 90 that you are adding, sine changes to cos. This is correct. Okay, cos theta can be written as sine of 90 degrees plus theta. Here we'll write it as pi by 2 plus theta. Now come back to the equations that we are deriving. The current equation we got in terms of cos. If you convert it to sine, you can write it as I naught sine omega t plus pi by 2. I'm writing it as theta plus 90. And we'll not use 90 here, we'll use pi. We'll write the angle in terms of radians. Okay. So omega t plus pi by 2. Isha, is this clear?
Yes, sir.
Okay. Now tell me, like a little bit of mathematics. Suppose time is 0. If t is 0, omega t will be 0. Then how much will EMF be at that moment? When omega t becomes 0, how much does the EMF become?
0, sir.
0 itself. Okay, because sine 0 is 0. Okay. So at t equal to 0, we see that the EMF will be 0. Fine. But substitute the same t equal to 0 here in the current equation. How much is cos 0?
1.
1. Then how much is the current at that time?
1.
The sine function, the cos function becomes 1. How much is the current?
I naught.
I naught. Current will become I naught. That is the peak value of the current. So I becomes I naught. That's the positive extreme. So when EMF is 0, see 0 is the mean value of EMF. EMF varies between -1 and minus E naught and plus E naught. No. So the middle value is 0. So when EMF is at its mean value, Okay, I should write it there. When EMF is at its mean value, current reaches its positive extreme. So tell me, are these two quantities in phase with each other? Are they
No,
reaching
sir.
their extremes at the same time? No. Isha,
No, sir.
Isha, what do you say? Do you agree with that or not? These two functions, the current function and the EMF function, are they in phase? Are they reaching their extremes at the same time? Okay. Clearly they are not. When one is becoming zero, the other is becoming positive extreme. So they means who? The current and the EMF across the capacitor have a phase difference. And how much is the phase difference? See, if you ever want to find out the phase difference between two functions, first ensure that the functions are written in terms of in similar terms. Ensure they are written in similar terms. The EMF function was taken as a sine function. Then you have to write the current also in terms of sine function. When we do that, we can clearly see the phase difference between the functions. Inside the sine bracket of the EMF function, you have omega t. But in the sine bracket of the current function, you have a pi by 2 extra, omega t plus pi by 2 extra. That itself is the phase difference between them. Okay. I don't know if you remember this or not. This bracket, whatever we write inside the sine or cos bracket, that itself is called the phase. Okay. So phase of the EMF function is omega t, whereas phase of the current function is omega t plus pi by 2. So current function has a phase of pi by 2 extra. Therefore, we say that current that flows through the capacitor leads the voltage we apply across it by a phase difference of pi by 2. Okay, so the voltage you apply across a capacitor and the current that flows through it will not be in phase with each other. They'll have a phase difference. And because the phase of current is pi by 2 extra compared to the phase of voltage, we say that current leads the voltage by a phase difference of pi by 2. Is this clear to both of you? Any doubts in this?
Yes, sir.
Okay. Let us visualize the graph also. Now this is the graph of y equal to sine x. Simple graph. So you can assume this to be the graph of the EMF function. E is equal to E naught or E is equal to E naught sine omega t. So the peak value will be E naught plus E naught. Minimum value will be minus E naught. And the time period, this will be pi by omega. This will be 2 pi by omega for this function. So that's how the EMF varies with time. Okay. And you should know how to understand these graphs also. Suppose an EMF graph is given to you like this. See, time moves in the positive direction. Time always increases, right? Initial time is 0. Okay. When time is 0, EMF is 0, as you can see in the graph. As time passes, okay, like let's say time becomes some 0.5 seconds. The EMF is becoming positive. Fine. So EMF is increasing. Then it will decrease, become negative. Then again it will increase and so on. That is what is happening with the EMF as time passes. Okay. Now the current function we got is a cos function, right? We got y is equal to, or I is equal to I naught cos omega t. So let's look at the graph of the cos function. Okay, let us adjust the graphs. 1 second. Just a moment. It's not working. I'm trying to get the y-axis lined up. Anyway, you can understand, I hope. So see, at t equal to 0, the EMF is 0. This point on the graph. The second graph is the cos function. This can represent the current for us. I is equal to I naught cos omega t. So the peak value will be I naught, positive peak. Negative peak will be minus I naught. Time period will be same. You look at the functions that we got. One was sin omega t, the other was cos omega t. Angular frequency is the same omega. So time period will still be the same for both the functions, 2 pi by omega. So, but observe what happens at t equal to 0, the EMF is 0, but in the current function at t equal to 0, the current is maximum. Fine. Now understand why we say that the phase difference between these two is pi by 2 and why we say the current is leading by pi by 2. Current is leading the EMF. Now on the EMF graph, you go by an angle of pi by 2 ahead. Okay, angle pi by 2 means omega t should become pi by 2, means go to a time of pi by 2 omega. A time of pi by 2 omega is this value. At that time, you see what is the EMF. It is at its positive extreme, right? It is at its maximum value. Whatever is going to happen to EMF at an angle pi by 2 later, that is happening with the current now itself. At t equal to 0 itself, it is happening. Okay. That is why we say current leads the EMF by a phase difference of pi by 2. Did you both understand what it means by current leading EMF by phase difference pi by 2?
Sir, so the current will always be pi by 2 more than like the
Ahead. You
EMF,
should say
right?
ahead, not more. Yeah, current will
Okay,
always be pi by 2, an angle of pi by 2 ahead of the EMF. Yes. Okay. Value may be more, maybe less, that we cannot say, but angle wise, it will be ahead of the EMF function. Okay. So this is what happens in a capacitor. When you apply an alternating voltage across it, the current through the capacitor will always have some phase difference with the voltage that you apply, and that phase difference will be pi by 2. Means when EMF is 0, current will be at its extreme. When current is 0, EMF will be at its extreme. That also you can see here in this graph. Like after 1/4 of a time period. Okay, I'll mark the points in which color? Let's mark in green. After 1/4 of a time period, current falls to 0. That is when the EMF becomes maximum. This value. Okay, 1/4 cycle ahead. Like if both of them move forward by 1/4 of a cycle, current falls to 0. EMF will go to its extreme value, positive extreme. We'll solve that in problems also. We'll see that in a problem. You'll understand. Next, look at the equation we got for current. I is equal to C E naught omega. Basically, this came from differentiation of charge. Charge was C E naught sine omega t. That's basically Q is equal to CV. Upon differentiating charge, we got the current equation C E naught omega cos omega t. So we get I naught, peak value of current, as C E naught omega. This can be written as E naught divided by 1 by C omega. Now, why do we do this? One of you quickly tell me, what is I naught? What is
Peak
the
current.
peak current? Correct. What is E naught?
Peak EMF.
Peak EMF or peak voltage, you can say. Let's call it EMF itself, not an issue. Okay. Basically, it's a voltage. Dimensionally, current should be voltage divided by what? Dimensionally, current is voltage divided by what, or which quantity? Right, tell Ohm's law. I is equal to?
V by R.
Then it should be voltage divided by a resistance. Okay.
Oh,
But look at what we have here. Instead of resistance, we have some other term here, 1 by C omega. So, like technically, this must be acting like a resistance, or this is analogous to a resistance. Now, in the circuit that we considered, okay, let me copy paste the circuit. There was a capacitor, there was a source of EMF, there was no resistance. Because had there been a resistance, you would have applied KVL and included resistance IR term in the equation. We didn't consider any resistance. Okay, so the regular resistance that we talk about, that is the what do you call collisions that the electrons undergo, that we did not consider at all in this case. Okay, so that regular resistance is not there in this circuit. But we got a term which is analogous to the resistance. What does that mean? Actually, resistance means opposition to the flow of current. And the usual resistance that we talk about is the resistance due to collisions of electrons. The opposition to the flow of current, which happens or which arises due to the collision of electrons with the conducting material. Here, this analogous resistance that we got, let's understand what it means. Suppose the charge on this plate of the capacitor is Q. Now look at what this current is doing. The current is trying to deposit some more charge on this plate. So current is basically flow of positive charge. So assume there is a positive charge going this way, and there is already some positive charge here already here on this plate. Will those two experience repulsion or not? The plate of the capacitor already has some positive charge, and you are trying to put another positive charge on it. Will there be repulsion? Will there be an opposition to that or not?
yes, so there will be a repulsion.
There will be. Okay, Isha, did you understand?
Yes, sir.
That is what is this analogous resistance that we get in case of a capacitor. So this 1 by C omega term is not actually the resistance due to collisions of electrons. Okay, this is the resistance offered by the capacitor in the form of repulsion. Okay, when you try to charge the capacitor, it will oppose the new charge from being deposited on it. Okay, so it kind of resists the current. And this term 1 by C omega, we don't call it resistance, we call it capacitive reactance. Okay, resistance offered by a capacitor. We call it as capacitive reactance, and the symbol for it is Xc. And dimensionally, it should be same as resistance. So the unit will be ohm itself. Dimensions also will be same as dimensions of resistance. Okay, but we don't call it resistance because this is not opposition to the flow of current due to collision of electrons. This is opposition to the flow of current due to electrostatic repulsion. Okay, so we call it capacitive reactance. Therefore, the peak current I0 can now be written as peak voltage E0 divided by XC, where XC is nothing but C omega. And we call it as capacitive reactance. Okay. So what all have we discussed? If you know how much is the EMF applied across the capacitor, you can write an equation for its charge. By differentiating charge, you will get the current. But now we learned that current maintains a phase difference of pi by 2, an extra phase of pi by 2 compared to the voltage. So now without taking help of charge equation, you can directly write the current equation. For example, suppose the EMF equation is given like this. Let's say 10 sine 100 pi t. E naught sine omega t. It's given in the standard form, easiest form. Let's say capacitance is some 20 microfarad. So C is known to us, E naught is known to us, omega is known to us. If you know C, E naught and omega, then you can write the peak current. Peak current is C E naught into omega. That can be written. And then you can write the current function itself. How to write the current function? Peak current. See, EMF is given in terms of sine. So here also you'll write sine itself. Current function, you'll write sine. But you know this is current through a capacitor. It should have a phase of pi by 2 extra compared to the EMF. So first write what phase the EMF has, add a pi by 2 inside. That's all. You can, like from the EMF or the voltage function, you can directly write the current function. Even if you first derive the charge function and then differentiate it, you will be getting the same thing. Is this clear to both of you? Any doubt in this?
Yes, sir.
Okay. You substitute all those values, you will get the actual current function. Fine. So in this case itself, you do the calculation. Tell me how much is the RMS current? See, the current function is a sine function. For sine function, the RMS value is 1 by root 2. So tell me how much the RMS value of the current will be. Also tell me how much is the capacitive reactance. Okay, solve it quickly, both of you.
Sir, what's the unit for RMS?
What unit?
Like there's no specific unit or something, right?
RMS value of a particular quantity will have
Oh,
the
it's
same
mean,
unit
it's
as.
me. Yeah, sir.
Huh.
So over here, if it's if what is the unit which we're using for this over here? Like
For what exactly?
so
Okay,
RMS
all
value will
wait. Assume all terms are in SI units.
okay.
Okay. Hmm. Okay, one of you tell me, how are you trying to calculate IRMS?
Sir, C E naught omega, which is 20 into 100 into 10.
Yeah, no, don't substitute values. C naught omega and then C naught omega is not IRMS. It is peak value of current.
Yeah, so I naught by √2 is IRMS.
Okay, correct. So since the current is sinusoidally varying, its RMS value will be peak value divided by √2. So in this case, it becomes C naught omega divided by √2. Substitute the numbers, you will get the answer. But remember, capacitance is 20 microfarad. Micro is a factor of 10 power minus 6. Minus 6. You have to keep that in mind. And you have to substitute that also.
Minus.
Okay, Isha, any doubt? Okay.
Sorry, sir.
Okay. Next is capacitive reactance. What is the formula for capacitive reactance?
Sir, 1 by C omega.
1 by C omega. 1 divided by C is 20 micro. So 20 into 10 power minus 6. Omega is 100 pi. No need to simplify. You can leave it like that. Or say 10 power 3, 10 power, you'll get a 10 power 3 divided by 2 pi. This will be in ohms. Reactance will have the same units and dimensions as resistance. Okay. Just a moment. Okay, let's use this graph itself. Across a capacitance of, let's say, 5 microfarad, an EMF given by this graph is applied. Okay, so instead of giving you the equation of EMF, I'm giving you the graph. So let's say on y-axis you have the EMF, on x-axis you have the time. I'll mark the values just a moment. The peak value of EMF, this value let's say is 10 volt. Okay, forget the numbers that are already written there. That maximum value is 10 volt. And let's say one time is given to you. Assume this time. One second. Okay, let's say this is given as 0.01 seconds. So you are given the sinusoidal EMF graph. So first thing I want you all to do is write the EMF function from this graph. Next, you know capacitance, you know EMF. Like once you write the function, you know the EMF. Then write the charge on the capacitor as a function of time. Okay, solve this much. One of you tell me, what is the general equation for alternating EMF? General equation for alternating EMF.
Sir, E naught omega, E naught
Tell
sine
properly.
omega t.
Okay, E naught sine omega t plus some constant also may be there. There may be a phase constant. Okay. So you have to, by looking at the graph or from the graph, you have to pick these values. How much is E naught? How much is omega? And is there any phase or is it matching with the sine function? You have to see. Has the sine function been pushed ahead, pushed back, or is it exactly like y equal to sine x? By looking at that, you can tell the phase difference. Phi naught or the initial phase you can tell. So think carefully and solve. How much is E naught peak EMF?
10 volts.
Okay, you can look at that from the graph. The graph, like the EMF graph, is varying between plus 10 and minus 10. That means the peak value is 10 volts. Okay. How to get omega from this graph?
Sir, so omega t is equal to 2 pi.
Omega and which t is 2 pi?
Like the time period of one thing is 2 pi, right?
Okay, omega into time period is 2 pi. Yeah, indirectly you are saying time period is 2 pi by omega.
Yeah.
Okay.
And then
Do you know the time period? Or can you get the time period by looking at the graph? From the graph. Isha, any idea for deriving omega?
No, sir.
Okay. See, omega is related to time period. T is 2 pi by omega. So if you know time period, you can tell omega value. One of you tell me the definition of time period. Basically, what does it mean?
like the amount of time it takes for one
One what? You say one oscillation. Okay.
yeah.
Huh. Or you can also say the amount of time after which the function repeats itself or the graph repeats itself. Now you can clearly see that there is a repeating part in this graph. For this part from 0 to positive extreme to negative extreme again to 0. This part keeps repeating, right? Look at the graph and tell me, or try to tell, what is the duration of each of these parts? Duration of each of these parts means what is the time interval from here to here?
0.01 into 4.
Correct. Correct. 0.01 is 1/4 of the cycle. So total cycle will be 0.04 seconds. Rishi, do you agree with this or not?
Yeah, sir.
Okay, you see the same happening here also. So after every 0.04 seconds, the EMF function repeats itself. So that's the time period. So from a graph, you can tell, at least if one interval is given to you, you can find out the time period. Okay. So Fine. You're only left with substitution now. Once you know time period, you can get omega. Omega will be done. The phase constant is what we still have to find out. The EMF function that you see here, the graph that you see here, is it like the regular sine graph or not? Starting from 0, going to +1, then 0, -1. Is it like the regular graph or not?
Yes, sir, it is.
Actually, it is. I took the graph of y equal to sine x only and made some modifications to it. That means the phase value here will be 0. So the EMF function is derived now. You get E in this form, 10 sine. Okay, let's quickly derive omega also. Omega is 2 pi by t. 2 pi by time period is 0.04, that is 4 by 100. 4 by 100 is like 2 by 50. 2 gets cancelled, 50 goes to the numerator, so it is 50 pi. That is omega into t, no phase constant. So we got the EMF function. Once you get the EMF function, writing the charge function is very easy. How do you write charge when you know EMF or voltage across the capacitor?
C E naught omega.
What is C naught omega?
Oh, sir, that's I naught, sir.
That's the peak value of current. I'm asking you how to get charge from capacitance and voltage.
Q is equals to CV.
Q equal to CV, correct. So C into the given, the derived EMF function you will write. Capacitance was given to you in the problem. That's all, you get the charge function. How do you write the current function if you are asked to?
V by R.
There's no R here, this is a capacitor. We know the EMF applied across the capacitor. How to get current passing through the capacitor or current flowing in the branch of the capacitor. What did we discuss today? From EMF, how to get current? Rishi, you tell, what is the derivation we did today?
Sir, alternate EMF across a capacitor.
Based on EMF and capacitance, we first derived charge in the derivation that we did. I'm not showing it to you. Try to recollect.
Yes.
After that, how did we get the current equation?
Current equation, we got I is equal to C E naught omega into cos omega t. And then after that, we found...
Wait. So I asked how we got the current equation. We got the current equation by differentiating the charge equation. We used I is equal to dq by dt. Okay, anyway, see, it's quite common that students don't immediately remember things. But you have to do all this derivation once on your own, not once, twice, how many ever times you need to do, you do, till you are able to derive these on your own. Okay, remember where we started from. We assumed a capacitance and an alternating EMF. That's all. Based on these two, we got the charge equation. That's the first thing we derived. You should be able to do that on your own. Next, from charge, since the wire is directly connected to the plate of the capacitor, we know current will be the rate of change of that charge. So I is equal to dq by dt gave us the current equation. That's the second thing we derived. And by comparing the EMF and current equations, we found the phase difference between them. That is the third thing we derived. And then I told you how to directly write the current function without taking help of the charge function. Okay, like in this question, the previous question. From EMF and capacitance, you can directly write the current equation. This is the fourth thing we derived today, or we learned today. You should be able to tell all this whenever you are asked. Okay, so tomorrow you won't have a class anyway, so take some time, maybe half an hour, 1 hour, and do this derivation. Do it as many times as needed, so that in such a way that you will be able to do it on your own whenever necessary. Okay, let's come back to this question now. We know the EMF equation, we know the current, we know the capacitance. We need the current function, current equation. Current equation will be of this form: I naught sine omega t plus some phase difference. I naught is C E naught omega, one of you just told. And with the EMF function, the current function should have, like compared to the EMF function, the current function should have a phase of pi by 2 extra. So write the phase of the EMF function first, 50 pi t, and add a pi by 2. That's all. That's the current function. If you want, you can differentiate charge equation and see you will be getting this itself. Okay. So based on the capacitance and the EMF that you apply, you know how to tell charge in the capacitor and current through the capacitor. Once you know charge on a capacitor, you should be able to tell the energy stored in it also. U is equal to, okay, I won't tell. One of you tell me, what is the formula for energy stored in a capacitor? There are 3 formulas. Tell me any one formula that you remember. Energy stored in a capacitor.
Sir, CV by 2.
What is CV for a capacitor?
Q, the charge.
Then CV by 2 will be
square by
CV.
2.
Oh.
Okay, it is. Isha, what did you say?
CV square by 2.
Half CV square. Okay, you may use that. In this case, you will write half C E square, the alternating EMF squared. You can also write, or you can also use Q square by 2C. Now you know how to derive the charge function, no? You substitute the charge function here, you will get the energy function. Can be done, but you don't have to do that. EMF is given, capacitance is given, you can use half C E square. Okay. So yeah, I want you both to do this part on your own. EMF equation, take it like this: E naught sine omega t. Okay, basic equation for EMF. Capacitance, keep it as C itself. So EMF is given, capacitance is given. Just substitute these two values, you'll get the energy function. Now see, E is being squared in energy. If you are squaring E, then the energy function will be something into sine square omega t. And you all know what is the average value of the sine square function. If you know average value of the sine square function, you should be able to derive average value of energy stored on the capacitor, in the capacitor. Okay, I want you all to do this derivation on your own. I'll send you a worksheet tomorrow with the steps. Okay, not exact steps, but like the same thing, what all you need to know to derive the average energy. Just complete it and send it back to me. Okay, so take some time, like half an hour, 40 minutes tomorrow. Do this derivation, even the derivation that we discussed in yesterday's class. Yesterday, we discussed what happens if alternating voltage is applied across a resistor. Today, we discussed what happens when alternating voltage is applied to a capacitor. And in between, we talked about something called capacitive reactance also. XC, that's the 5th thing we discussed today. Try to recollect the meaning of capacitive reactance. Don't blindly remember. Okay, I'm sure you all must have heard these things in your school when you learned this chapter, when you went through this chapter. But clearly you don't remember much. That is because you don't do the derivations on your own. You don't try to understand the meaning of things. So physics requires little bit of patience. You have to work, you have to understand thoroughly, like, and when revising notes also, you can simply revise it as capacitive reactance and leave it like that, but that won't help you in the final exam. You should recollect the idea that we discussed. How can a capacitor offer resistance? This is not through collisions. This is through repulsion of charge. So, like if you think deeper, then automatically you'll be spending more time with the subject. Automatically your chances of remembering will increase. You will remember the subject better. Okay, so practice all these derivations. Next class will be on Thursday. Thursday we'll discuss alternating voltage applied to an inductor. Okay, and if time permits, resistance, capacitor, inductor, all three together also. If you apply an alternating voltage, what will happen? We'll see LCR series circuit. Okay, thank you all. We'll continue on Thursday.
Thank you, sir.